I think we want to usually wait a few minutes, and so maybe let's takes 1 or 2 minutes wait. Okay. All right. So let's see. So maybe I will start to introduce the speaker. Right. So I'm very happy to introduce today's colloquium speaker, Ankur Moitra. And he graduated, he has a PhD in computer science from MIT in 2011. His thesis works actually won the year's Best Thesis Award in EECS. And he works on many areas in theory, computer science, and mathematics. And that's so he actually is a professor in mathematics, statistics, and computer science. So, so in the past few years, he has been working on algorithmic and the mathematical aspect of machine learning. So he actually has a book of almost the same titles. So one of the problems he solved is it's actually a famous Gaussian mixture problems, which actually dated back to Pearson's work in 1894. So it's a remarkable old conjecture. He also received a Packer Fellowship and many other awards. So I will not go into details here, and let's welcome Professor Ankur Moitra. All right.
Right, so thank you. Yeah, thanks everyone for coming. So I'm excited to tell you a little bit about my work through an agenda that I'm very interested in. So this talk today, I'll be focusing on problems in high-dimensional robust statistics. Now, these are older questions, but I'll be talking about how to revisit them from an algorithmic and mathematical perspective. So I'll give you the first provable algorithms for robustly estimating the mean and covariance in high dimensions. Now, I have pretty modest goals because I know that people come from pretty different backgrounds. So I'm not going to start with high-dimensional robust statistics. Actually, I'm not even going to start with robust statistics. Maybe let's just start with statistics, because really it's important how these questions are set up. So there's an entire area of problems in statistics called parameter estimation. And roughly it works as follows. You're given samples from an unknown distribution, but it lives in some nice class of distributions. So the canonical example you should think about for this talk is the 1D Gaussian. So I know my samples are coming from a 1D Gaussian, I just don't know its mean mu and variance sigma squared. Now you can ask, can we accurately estimate its parameters from few samples? And the answer is a duh, of course you can, because all you have to do is take the empirical mean. You just take a bunch of samples, you take the empirical average over them, and that'll converge very quickly by the central limit theorem to the unknown mean mu. And same thing works for the empirical variance. Now here, x bar is the empirical mean, and that's going to converge very quickly to sigma squared. So this is classic parameter estimation, and these are really two examples of a more general paradigm that was started by Fisher in the 1910s and 1920s, which is called maximum likelihood estimation. So those parameters, those estimators, the empirical mean and the empirical variance, are the answers to what setting for the unknown parameters is most likely to have generated the data that I actually observed. And there are lots of wonderful properties about maximum likelihood estimation. So it's known, for example, that under certain technical conditions, that as you take the number of samples going to infinity, it always converges to the true unknown parameters. In fact, it's asymptotically efficient in the sense that it converges at the fastest possible rate. Now, that's not really what I'm going to be talking about. It's instead starting from this beautiful question of Tukey, which is such a basic question that it honestly could have been asked much earlier. So we know that when our samples come from a nice model, what's the best estimator? But what happens when that assumption is really just a simplifying assumption? So what if there are errors in the model itself? And that's really the starting point of robust statistics. So I want to explain this caricature of what types of problems robust statistics ask. And I want to make sure that they're mathematically set up properly before we go into high dimensions where we'll have interesting algorithmic problems to solve. But the basic setup for robust statistics is same kind of thing as before. You have some idealized model. You don't know its unknown mean mu and its unknown variance sigma squared. But now the catch is that someone adds some small amount of noise, and what you actually get samples from are the thing on the right-hand side. That's the observed model. So it might look close to a Gaussian, but it's not exactly a Gaussian. And the basic question in robust statistics is, what can you do in the face of this noise, in the face of this model misspecification? Are there still algorithms and estimators that can accurately estimate the unknown parameters? So let me make this precise. So the first question is, how do we constrain the noise? Now, there are actually a few different ways of thinking about how we might constrain the noise. They turn out to be equivalent up to constant factors, which is nice. So one thing you can do is you can take that little red tittle that I added on top, and I could constrain its L1 norm. So I could say that that little twiddle of noise is O of epsilon in L1. Or alternatively, I could think about it as allowing an adversary to arbitrarily corrupt some fraction of the samples. So the way to think about the relationship between these two different views is that when I take the two curves, the blue idealized curve, and overlay it with the green actual curve that I get samples from, while the region where the green curve is above the blue curve is where an adversary is injecting new samples. And the region where the green curve dips underneath the blue curve is where the adversary is deleting samples. So we can think about, the model for noise as an adversary is allowed to arbitrarily corrupt some epsilon fraction. Think epsilon is 0.1, so 10% of our data. And this is related to things like the Hubert contamination model. So let me briefly mention that in case you're interested in the distinctions between all these models, we're actually going to work with the strongest possible one, which is the adversary will be allowed to look at all of the samples and then decide which actual samples to corrupt. But I'm not going to dwell on the differences between these things. And let me introduce just a little bit of nomenclature. So I'll refer to the points that the adversary has tampered with as outliers, and the inliers are whatever is left over. They're the points that he hasn't corrupted in any way, and they did come from some nice distribution. So this is the first part of making the questions around robust statistics precise. Now the remaining question is, well, we have our model for noise, but what makes an estimator good? So in what norm do we want our parameter estimates to be close to the truth? And the natural thing to do is to use basically the same norm, the same distance that we started off with, where we allowed the adversary to make corruptions. So you can talk about the total variation distance between two distributions. That's just half of the L1 between their PDFs. And the way to think about it is, what has the adversary done to our nice idealized Gaussian model? Is the adversary has moved it from being exactly a Gaussian to some other distribution that's O of epsilon close in TV. So the natural goal is to try and find a 1D Gaussian that's close to the idealized model in the same distance measure. So we started off being epsilon close to a Gaussian, and maybe I want to estimate this orange curve, which is 3 epsilon close to the thing I started off with. So in that sense, I would be designing an estimator that's provably resilient to an adversary having control about some amount of the data. Or I could think about it as merely fitting the truth with some nice economical model like the Gaussian, because I'm equivalently finding a 1D Gaussian that satisfies these TV estimates. Sweetie, sorry, my kids are sick, so they're both at home. Sweetie, you have to go outside, okay? Okay, can you go find mommy, please? Sorry. Sweetie. Okay, so the first question I have to answer is, do the empirical mean and empirical variance work? So here the answer is a resounding no, because these were the things that did work when we didn't have any corruptions over our data. But as soon as you allow an adversary to corrupt some fraction of the data points coming from our model, well, we can't get any nice guarantees, because even if an adversary could control just a single sample from our model, what would they do? Well, they would add a bump way out into the tails of the distribution. And then what would happen is, if we take the right-hand side, if we take this observed model, then as we move the bump further and further away from the center point of this distribution, the empirical mean is going to go arbitrarily far away, and it won't actually be a good estimate of the truth. So how are we going to fix this particular model? Well, instead, what we're going to do is instead of the empirical mean, we're going to use the median. So now the nice thing is that, once we take the median, when we add that epsilon fraction of corruptions in the tails, then in fact, we're not going to pull the empirical median too far away from where it started off with. And now if we want to fix the empirical variance when a single corruption can mess it up, what are we going to do? Well, we can instead use a median of medians. So if the median worked once, let's use it again. So what we do is we take all of our samples, we take the empirical median, and we take the median of all of those absolute values of differences, and that's called the median absolute deviation. So the folklore fact from robust statistics is that if we're given samples from a distribution that's not actually Gaussian, but is merely epsilon close in total variation distance to a 1D Gaussian, then what we can do is we can compute the median and the median absolute deviation. Those estimates mu hat and sigma hat are going to have the property that they define a Gaussian that's O of epsilon close to where we started off from. So we need some sort of corrective constants depending on what's actually going on here. But just to put this in perspective, yeah, sorry about the interruption. My daughter got sick and she's now out of the room. So back to normal. So in fact, this is the best of all possible worlds. If you think about what this guarantee means, first of all, it's provably robust because we're allowed to have any epsilon corruption and we can tolerate that. We start off epsilon close to Gaussian, we end up 3 epsilon close to the Gaussian we started off with. So that's great. It's also statistically efficient. If I wrote down the sample complexity, it turns out to use the optimal number of samples up to constant factors. And in fact, it's also algorithmically efficient. So how would I compute the median and the median absolute deviation? I just compute them because they're in 1D. So now I come from theoretical computer science, and in my nomenclature, these things would be called properly agnostically learning a Gaussian. So first of all, it's agnostic learning because you're no longer making some sort of religious belief that your samples really do come from a Gaussian. You're merely saying that if they come from something that's close to a Gaussian, you want to do very well too. And it's also a proper estimate because you want your estimate to actually come from within the class. So you start off with samples from a 1D Gaussian, and I spit out the mean and variance of another Gaussian. And now I can get to the main point of this talk now that we understand the basic setup of robust estimation in 1 dimension. I want to study the problem of robust estimation in high dimensions. And here we're going to have some interesting surprises because all of a sudden, we can't take for granted that the estimators that we want to compute, we actually can compute. So that's the big punchline, is that there's going to be a tension between being computationally efficient and being provably robust, even for very basic problems. So the example that I want you to keep in the back of your mind, and I'll show you some real data examples at the end, are in a lot of modern data analysis settings, we frequently are dealing with very high dimensional data sets. And the dirty secret is that we don't understand how a small amount of model misspecification derails even simple estimators that we want to use. So let me tell you about the question that I'm really going to care about in this talk now that we've set up the language of what robust statistics is and what sorts of noise models we're interested in, which is actually the same question that I've already introduced you to, except that it's happening in D dimensions. So again, we're given samples from a distribution that's not exactly Gaussian, but it's epsilon close in total variation distance to being a Gaussian. And what I want to do is I want to give an efficient algorithm to spit out parameters mu hat and sigma hat that's O tilde of epsilon close to what I started off from. Now, the only difference is that now mu is a D-dimensional mean vector, and sigma is a D by D positive semi-definite covariance matrix, right? But just to emphasize, setting up this problem the right way makes things a lot easier. Because, in 1 dimension, there's a lot of choices for how exactly you measure the closeness of the parameters you started off with and your estimates. It doesn't matter that much in 1D which parameter distance you choose, but in high dimensions, it matters a whole heck of a lot. Because when I think about, on the one hand, sigma, which is my unknown covariance, and on the other hand, sigma hat, which is my estimate of it, Those are matrices. So do I want to measure their closeness by looking at the Frobenius norm of their difference, the spectral norm of the difference, the nuclear norm, whatever you want? Those are all valid choices that are often off by poly and D factors. So if we choose the wrong one, then we can make our problem completely trivial or impossible. But by setting up with total variation distance, which naturally captures this model where the adversary is corrupting some constant fraction of our data, we naturally have, the strongest possible distance function and something that's also affine invariant. So there'll be two special cases because I want to discuss what was known before our work. So I could make your life easier, and I could promise you that the unknown covariance matrix sigma is the identity. Then all you have to do is estimate the high dimensional mean mu. I'll call that the unknown mean case. Or alternatively, I could make your life easier by promising you that the unknown mean is 0 and just saying that you have to estimate the high dimensional covariance sigma. So these two cases and the nomenclature of robust statistics would be called robust estimates of the location and scale, respectively. So let's keep it simple. So what was known even in the case of just the unknown mean? So the covariance is the identity. So really a Gaussian looks like a high dimensional root D radius ball. And I just want to estimate the center of this ball in a way that I'm robust to some constant fraction of errors. Now in 1D, remember the way that we did it was we used the empirical median. So the natural thing you would try is to use some high dimensional generalization of the median. And you can do that. There's something called the Tukey median, which it's not so important for the purposes of this talk how it's precisely defined. So let me just define it in words, but not actually spend much time on it. Well, what you do is if you're given a cloud of points, you can talk about the Tukey depth of a point as the worst case over all projections about how few points are either to the right or left of it. So that's the Tukey depth, is the min over all 1D projections of how few points are to the right or left of it. So how close it is to the extremes. And what you do is you take a bunch of samples from your high dimensional distribution, and then you look for the point over all space, which is the Tukey deepest. And intuitively, that'll be in the center of your distribution, and that will be a provably robust estimate for the unknown mean. In fact, you can prove wonderful properties about this estimator, because if an adversary corrupts an epsilon fraction of your data, it's a wonderful estimator because it'll get you O of epsilon close to the thing you started off with. But now there's a big catch, right? Which is that unfortunately it's NP hard to compute. Now what this means concretely is that the best algorithms that we know of for computing this with n points and d dimensions run in time n to the d. So despite the fact that the Tukey median has been known since the 70s as being something great that we would want to compute, I have never seen it successfully computed beyond dimension 6. So that's the thing that's missing in high dimensional robust statistics and high dimensional machine learning, is we know in principle these kinds of robust estimators are out there, we just can't actually compute them. So the next thing you might wonder is, maybe I chose the wrong generalization of the median from 1D to high D, right? So the other thing that I could do is I could do something naive, like I could take the coordinate-wise median across each of the coordinate problems independently. That's obviously solvable in polynomial time because it's just D different one-dimensional median problems. But there's a big problem with this, which is you start off epsilon close to the Gaussian, you only end up epsilon times root D close to that Gaussian. Now, intuitively, why is this the case? Is because a Gaussian looks like a ball of radius root D. And in fact, the direction the adversary might have added the corruptions might not be aligned with any particular coordinate axes. So when you solve those D one-dimensional median problems, you might completely miss the directions in which the adversary has added the corruptions because of concentration of measure. So you can do this exercise for all of the estimators that have been proposed within robust statistics. Since its inception, this is one of the most basic problems there, and everything has exactly this tension. There are things like the tournament estimator that would be great if you could compute them, but you can't compute them beyond dimension 6. And there are naive estimators that you can compute whose guarantees really go out the window once you talk about any high dimensional problem. Now, epsilon times root d is a horrible guarantee for reasons that I'll get into just on the next slide. So let's talk about this issue. Now, in my field, we love naming these things as the price of, right? So maybe this is just some kind of price of robustness. This is some kind of steep price we pay for deviations in our model. Because just to summarize, all the known estimators, even for the most basic problem, estimating the high dimensional mean, are either hard to compute beyond dimension 6, or they lose polynomial factors in their dimension. Now, why is this such a horrible guarantee? Is because the total variation distance between two distributions is only ever at most 1. So when are we getting non-trivial guarantees on how well we can estimate in the face of corruptions is only if the fraction of corruptions is decaying at an inverse polynomial rate. Even though we know in principle it ought to be possible to get estimators that can tolerate a universal constant fraction of errors that's completely independent of the dimension. Just to be concrete, even if I had no hidden constants in these guarantees, for simple 10,000 dimensional problems, which aren't even that big dimensional to be perfectly honest, that means we can only tolerate some tiny, minuscule 1% of corruptions. So unfortunately, in theoretical computer science, a lot of times when you prove something is hard, you're stuck, right? So you might wonder, is robust estimation even algorithmically possible in high dimensions? So the good news is that the answer is yes. So I'll walk you through some of the main intuitions behind this theorem and some of the main mathematical ingredients, but let me give you a quick summary of the overall results. So there is an estimator that achieves the best of all possible worlds. So what it does is you're given samples from a distribution that's epsilon close in TV to a high dimensional Gaussian. It takes a polynomial number of samples and it runs in polynomial time. And it spits out estimates that are so good that they avoid all dimension-dependent factors. So there's an extra polylogarithmic term in 1/epsilon, but it gets you almost epsilon close to the unknown distribution. So that's what I'll be sketching out, some of the main ingredients in this. One of the nice things about this was that this was really the starting point of a bunch of work in this. So this paper is back from 2016, and there's actually couple hundred papers on this already, but you can do all kinds of nice things, like you can, for starters, weaken the assumptions from being Gaussianity to sub-Gaussian or bounded moments, albeit you get weaker guarantees. I'll mention that at the same time, there is independent concurrent work of Lai, Rao, and Vempala that got these kind of error guarantees. So they have some polylogarithmic dependence on D. They get a worse dependence on epsilon, so it's root epsilon. Now, these don't actually translate to total variation bounds because they're not affine invariant. When I apply affine transformations to my distribution, it's still a Gaussian, but then the spectral norm of sigma changes so that the guarantees degrade. But if you have the right extra assumptions, like the covariance being bounded, it translates into this root epsilon type of guarantee. But as I mentioned, this was really sort of the levee breaking in some sense for reasons I'll get into. But there are all kinds of extra things you can do once you know that you can do some things in high dimensional robust estimation. You can do things like you can ask what happens if an adversary is allowed to corrupt more than half of the data. That sounds like, that question isn't going anywhere, because if they can corrupt more than half of the data, why couldn't they just add a spurious extra Gaussian and you would never know which one is which? Well, you can still do things like outputting a small list of hypotheses, one of which is guaranteed to be close to the true answer. That's called list decoding. And you can do that with error rates that are approaching 1. You can give lower bounds against classes of algorithms and show that this epsilon versus epsilon times polylog 1/epsilon is an inherent tension between robustness and computational efficiency. As I mentioned, you can weaken the distributional assumptions. You can do things like you can marry ideas from compressed sensing and study what happens when you have extra sparse priors on your distribution. That creates some interesting things related to restricted isometry property and some nice geometric problems. You can even work with more complicated generative models, things like independent component analysis, that are used to disentangle overlapping speech patterns in a room when you have a single microphone. And I'm not going to say more about that because I really just want to give you a flavor of what goes into these algorithms. Because the cool thing, I think, is that it's a very simple general recipe once you see it. So in fact, there's a general recipe that all of these works follow. And it's just the following 3-step procedure. And I'll walk you through it on 2 examples, the unknown mean case and the unknown covariance case. Now, the first step is going to be we're going to find an appropriate parameter distance. That'll be a good surrogate to working with the total variation distance. Then in step 2, we're going to do something more naive than Tukey tried. See, Tukey tried to design an estimator that always works, the Tukey median, and he got tripped up because it was hard to compute. What we're going to do is something more naive. I told you that the empirical mean doesn't work. We're going to use it anyways. But the catch is that we're going to be adaptive. So we're going to detect when that naive estimator has been compromised. And we're going to use spectral and then later tensor spectral methods to detect these kinds of things in high dimensions. That's the main technical ingredient in this. And then we'll have a simple win-win algorithm because either we'll find provably good, provably robust estimates of the parameters, or we'll find some large collection of outliers that we can throw out from our data and recurse. So let's start off this recipe in the simplest possible case, which is the case of the unknown mean, which remember is the case where I promise you that the covariance is the identity. So the Gaussian looks like a ball, and all you have to do is find the center of the ball in a way that's robust to a constant fraction of corruptions independent of the dimension. So let's see how this works. Step 1 is very formulaic. It's kind of the only thing you can do. So I want to find a parameter distance that's easier to work with than total variation distance. I argued when I set up the problem about why total variation distance is the right thing, but now let's work with something that's a bit analytically easier to wrap our heads around. So what I claim is that if you have 2 high-dimensional Gaussians and they both have the same identity covariance, that the total variation distance between these 2 Gaussians is related to the Euclidean distance between their means. Now, before I tell you, why these types of things are true, this is a fairly intuitively obvious statement because when I have 2 high-dimensional Gaussians, the only differences between these 2 Gaussians really occur along the line connecting their centers. So this is completely a 1D problem. But the way that you prove these things is there's something called Pinsker's inequality that relates the total variation distance to the KL divergence between Gaussians. The nice thing is that the KL divergence between Gaussians has a nice closed form expression. So all you have to do is plug in the parameters here and invoke Pinsker's inequality. And it tells you exactly this bound on the total variation distance, which just lets us reformulate our problem. Remember, our goal at the end of the day is to remove dimension dependence in these robustness guarantees. And now our goal is just to be dimension independent when we want to estimate the mean in Euclidean distance. So this is a nice geometric problem. So, let's move on to the main step, which is really doing something more naive than Tukey tried, which is let's just try and use the empirical mean anyways. So remember what I've been telling you is that, a high-dimensional Gaussian with identity covariance, well, it looks like the uniform distribution on a thin spherical shell where the ball has radius root d. So what would the adversary do to drastically corrupt the empirical mean? Well, the adversary might choose some direction and add all of their budget of corruptions along that direction. So even though there's only an epsilon fraction of the points that are corrupted, because they're root d away from the unknown mean, then they actually move the empirical mean by epsilon times root d. Now, the key point is that I don't see which points are black and which points are red. So I can't ever hope to perfectly figure out which points are corrupted and which points aren't corrupted. But at the very least, if the adversary did mess up my naive estimator very badly, there would be a method of at least detecting that something has gone wrong. Because when I'm in this unknown mean case, I'm operating under the promise that the covariance is the identity. So along every 1D projection, my variance is supposed to be 1. But the trouble is that when the adversary adds this budget of epsilon corruptions that are root d away from the mean, well, along that direction, connecting mu and mu hat, then, when you project along that direction, the variance is much, much larger than it should be. That's it. So what's the key lemma that you can prove is that if you take samples from a distribution that's epsilon close to a spherical Gaussian, and you take about d over epsilon squared samples, which is within a constant factor of the information theoretic minimum, then what you can do is you can take the empirical mean of that distribution and the empirical covariance. And the key fact is that if the empirical mean is off, so if the Euclidean distance between mu and mu hat is too large, it's 100 times epsilon times root log 1 over epsilon, then that's actually going to mean that the covariance is off too. That if you look at the spectral norm of sigma hat minus the identity, that's going to be too large. It'll be at least C prime times epsilon log 1 over epsilon. So the main takeaway here is that in order for the adversary to corrupt the first moment, they actually need to mess up the second moment too. So now we can turn this into an algorithm. I want to emphasize that the algorithm itself is very simple. The analysis is not, for reasons that I'll get into. But what is the simple win-win algorithm? Well, either we're going to find provably good estimates of our parameters, or we're going to find a direction we can project on where we'll be able to remove many points, most of which are outliers. So in the case where sigma hat is close to the identity, we're done, because the converse of that key lemma would promise us that mu hat is close to mu, and we could call it a day. But what happens when they're not close? So what happens when the spectral norm of sigma hat minus the identity is too large? Well, the only reason that the spectral norm of sigma hat is too large is because there's a direction where the variance is larger than it's supposed to be. So if I project on that direction, well, the intuition is that the reason the variance is too large is because of the corruptions. So what you can show is that there is some threshold t, and there's a formula you can write down for t, so that on this direction of largest variance of the empirical distribution, if you throw out everything that's above this threshold t, you're going to throw out many more outliers than inliers. Now, some inliers get thrown out too, and that's not good, but for every inlier that you throw out, a black point, you throw out at least 2 corrupted points along the way. So you're making progress, because whatever is left over has a smaller fraction of corrupted points. So this is the win-win algorithm, because if this procedure didn't terminate, eventually we'd run out of corrupted points to throw out. So at the end of the day, we find certifiably good parameters in not too many iterations. And you can work out what the running time of this is. It's a very reasonable running time because you're just doing a bunch of top eigenvector computations, no big deal. Now, the sample complexity is a bit more subtle to work out, as is the proof of correctness, because the real subtlety here is that in the first phase, the corruptions the adversary adds might affect which of the inliers you throw out. So then in the next phase, all of a sudden you have to contend with the fact that the remaining inliers are no longer independent and identically distributed, because they have some dependence on what the adversary did in the previous rounds. So in order to actually analyze these things, you need the right pseudo-randomness properties of your distribution, and this relies on things like concentration properties of linear threshold functions over Gaussian space. So this was the simple version of the recipe, but I want to convince you in the time that's remaining that this is a very powerful recipe. This is why all of a sudden, robust statistics is within reach algorithmically. And let's study the harder case, which is the unknown covariance. And now we'll get into tensor spectral methods. So remember, we want to follow the same recipe. We want to find an appropriate parameter distance. This is pretty methodical. There's nothing interesting really there. There'll be the same trick. The interesting thing will be how exactly do we detect when the naive estimator, the empirical covariance, has been compromised. So just as a reminder, the unknown covariance case, I'm promising you that the mean is 0. And all you have to do is figure out a good estimate sigma hat. So first, I want to find an appropriate parameter distance. And I can do the same type of thing that if you again use Pinsker's inequality and you come up with an upper bound on the total variation distance, this turns out to be the right expression. If you have two Gaussians which both have 0 mean, and you want to know how close they are on TV, well, you want to use this expression on the right-hand side, which kind of looks like the ratio of their variances in all directions. This is called the Mahalanobis distance. It's proven using Pinsker's inequality. And if you remember back in the beginning of the talk, I gave you this teaser that you have to define these problems in the right way to make them possible or not trivial. So when I asked you what's the right distance function to measure the distance between sigma and sigma hat, I suggested maybe the Frobenius norm of their difference, maybe the spectral norm of their difference. It turns out this Mahalanobis distance is actually the right thing, because that's the only thing where you'll be able to remove these dimension-dependent factors. So that's our new goal, is we just want a provably robust estimate for the covariance that satisfies that the Mahalanobis distance is O tilde of epsilon. That's our goal. Distance seems strange, but I claim it's the right one to use. So now let's do a thought experiment, because this one I'll have to sketch a little bit more. So let's imagine we're given samples from a high dimensional Gaussian, but it's n of 0i. Well, one of the things you might wonder is how can we detect when the naive estimator has been compromised? So when is sigma hat really far off from what it's supposed to be? So the key identity is the following. So if you remember back in the unknown mean case, the idea was we want to detect when the empirical mean has been compromised by looking at the empirical covariance. So here, to detect when the empirical covariance has been compromised, I need to look at the fourth order moments. I need to look at the fourth order tensor. And what I'm going to do is I'm going to flatten it into a d squared by d squared matrix. That's what this fact is doing, is it's telling me the structure of what I get. So imagine I take samples from n of 0i, and then I form this d squared by d squared matrix, where I take a sample x sub I and I tensor it with itself to get a length d squared thing. And then I take it times its own transpose, and I take the average over the distribution. That matrix M is a d squared by d squared matrix. And if you restrict it to the right subspace, it has a very elegant and useful form. It's 2 times the identity tensored with itself times this, which is I flat. So what I mean by this symbol is that you take the d by d identity matrix and you flatten it into a length d squared vector. And you take it times its own transpose. Now this, turns out to not be a very hard thing to prove. It's proven using something called Isserlis's theorem or Wick's formula. I'll give you some intuition, but it's a little bit outside the scope of this talk. The intuition for it is, if I take a 1D Gaussian with mean 0 and variance 1, you can check on Wikipedia, the fourth moment is 3. Now it turns out that, and it's no coincidence, if I take a complete graph on 4 nodes, there are 3 perfect matchings. And there's actually a very strong relationship between the number of perfect matchings in a graph and the moments of a high dimensional Gaussian. And that's where this expression comes from. That's what Isserlis's theorem and Wick's formula do, is they give you a precise relationship. And the important thing here is that there are really 3 terms. There are 2 terms that look the same, 2 times the identity tensor with itself, and something that looks a little bit strange because it has this flattening. That really comes from the fact that I'm taking 4 copies of x sub I, but one pairing of them is a little bit different, because one pairing goes along the 2 things that are mated along the rows. And that contributes something a little bit different, and it contributes to this I flat. Now, why I'm dwelling on the structure of this matrix is that if you think about it, the spectral norm of identity tensor with itself is 1, because it's still the identity. But the spectral norm of this I flat piece is now a polynomial in the dimension. So if I'm not careful, an adversary could hide some polynomial in D, dependence in my robustness in the shadow of this much larger contribution to the spectral properties of M. So the key here is that there's a way to project this out. Because instead of looking at all quadratic forms on M, I can look merely at quadratic forms on M and optimize over them that are themselves vectors that are flattenings of trace zero matrices. And if I do that, then I'm essentially projecting out this much larger term. So instead of looking at the spectral properties of M, I instead look at the restricted eigenvalues of M, and that'll allow me to detect corruptions in the second moment by working with flattenings of the fourth order tensor. So, how does this overall algorithm work just as a sketch? Well, what you do is you try and do the same thing as before. You try and use your naive estimator, sigma hat. And you transform the data. So you apply sigma hat to the -1/2 to all of your new samples. And if sigma hat were a good estimate for the unknown covariance, then this would look like samples from n of 0i. So in particular, I could set up that same matrix I had before. I could look at the restricted eigenvalues of it. I could subtract off 2 times the identity. And what you can show is that if the restricted eigenvalues of this new matrix are small, it must mean that sigma hat is close in Mahalanobis distance to sigma. And if it's not, it gives you a direction, albeit a space of degree 2 polynomials, where you could find many outliers and throw them out. So that's the key idea, is that it's actually the same type of approach as before. In order for the adversary to corrupt the second moment, they actually have to mess up the restricted eigenvalues of the fourth moment too. So this allows you to actually detect, through higher moments, more complicated corruptions. This is why these ideas have, many people have been working in the space and found lots of beautiful applications, is because moments are a very powerful way to estimate distributions. And now all of a sudden we have a recipe for how exactly to take that old recipe and make it be robust. So let me briefly tell you about how to assemble the overall algorithm. So what happens if I want to solve the full problem, right? So I'm given samples from some distribution that's close in TV to a d-dimensional Gaussian, but I don't know its mean or covariance. So now what I can do is I can actually reduce to the 2 cases we studied before. So I can take twice as many samples. And now when I look at xi minus xi prime, well, the means will cancel, the variances will double. So these will look like samples that are close to coming from a Gaussian n of 0, 2 times sigma. So now I can robustly estimate the covariance, and I can find some estimate sigma hat. I can apply sigma hat to the -1/2. That'll be like putting something in isotropic position. And now I'm back in the case where I want to estimate the unknown mean. It turns out that this is even the right distance to estimate the unknown mean, because in a direction where you have small variance, that's where you really have to get the mean correct. So when you put these things together, then you get the overall algorithm. You get something that gets you O tilde of epsilon close to the unknown Gaussian with no assumptions on how the adversary has spent the epsilon fraction of their corruptions. You get a provably polynomial time algorithm of provably polynomial sample complexity. So, in my neck of the woods, I spend a lot of time doing exactly these kinds of things where I want to formulate some basic problem in machine learning and statistics and computer science, which hasn't been solved before. Maybe it hasn't even been articulated that way before. And I want to design better algorithms by connecting it to mathematical tools. And ultimately, the end goal is to also have it lead to new ways of doing things in practice. And I think that for me is the exciting part. Is I don't think of theoretical machine learning as merely trying to predict what machine learning is doing and explain it away using toy models. I want to study basic problems that incentivize me to design new ways to do basic things. So let's see how these things actually work. I told you that it's now possible to robustly estimate high-dimensional Gaussians, something that people have wanted to do since the starting point of robust statistics. Let's first try it out on synthetic experiments, right? So let's create our own data set sampled from a Gaussian and add our own noise. at first I thought when we were doing these experiments that I would have to do something, a little bit dubious to, or I would have to work hard to figure out what kinds of corruptions mess up existing things. It turns out very simple corruptions mess up everything that people had proposed. All you do is exactly what you'd think. You shoot off in some random direction. You add your 10% noise right on the boundary of the Gaussian, and you can see what happens. So there are old methods. There's something from the 1970s called ransack, which actually has tens of thousands of citations. So it's something that people use all the time. They think it works, but it merely works in low dimensions. So if you plot how well ransack works in terms of how well it can estimate the unknown mean, it becomes terrible. So it becomes almost trivial, because 2 will be trivial. It becomes almost trivial even when you're in dimension 100. So these are things which, even though they're widely used, do not actually work. So it's kind of funny. Right down here is the filtering algorithm that I told you about. It's this black curve down here. This blue one is the Lai-Rao-Vimpala algorithm. And you can see that we're very clearly getting dimension independence for the robustness. What happens when you want to estimate the unknown covariance? Well, there are 2 cases you can study. One is where the covariance is close to being isotropic. So imagine that, there's no directions where the variance is much larger than it is in other directions. So the ratio of variances in different directions is bounded. So it's close to isotropic. In that case, you can do the same type of thing. There's no surprise, ransack is terrible. We do quite well. This is the black curve down here. And something really funny happens, which is, when you study the anisotropic case, where you have directions where the variance is much larger than it is in other directions, you can all of a sudden see the differences between how well you can do estimation when you have affine independent guarantees versus, when you have something that isn't affine invariant, like this Lai et al. Approach. This is level 1 of sort of justifying why these algorithms are cool. Let me take it a little bit further. This is really the experiment that I personally really enjoyed. See, at the end of the day, these problems about high-dimensional robust estimation of Gaussians, they're meant as an approximation to the truth. So we don't believe that all high-dimensional distributions are Gaussian, but the important thing is that these high-dimensional distributions have Gaussian-like projections in 1D. And what we really have we have tensor spectral algorithms for finding non-Gaussian projections to filter out the outliers. So what happens when we work with real data, which is really not Gaussian? So let me tell you about a cool experiment that comes from biology. So there's this famous work of November et al. So what they did was they took a genetics experiment, the Papyrus project in the NIH, which is an experiment where you have a whole bunch of people who you fully sequenced. So you know their genes down to the SNPs, right? And what you do is you form a giant matrix, which is people by SNPs. So each column is a person and it's their full genetic information. And what you can do is you can take this giant matrix and you can take the top 2 singular vectors of it. Now, what that means from an optimization standpoint is you're taking your high-dimensional data set, the people as vectors over their SNPs, and you're asking what 2-dimensional projection maximizes the variance. And when you project the data on those 2 directions and color code it with where those people are from, you get the map of Europe, which is pretty amazing. So this is called genes mirror geography in Europe. Now, if this is the first time you're seeing it, it's kind of wild. It makes some sense because, what should be the directions of largest genetic variation? Well, they should probably be geographic because things like the average temperature are certainly a big driver of genetic variation. So that would be thermocline. And then you can expect that there's some sort of impediment to mixing, across large scales. But this was a very, very cleaned data set, as you can imagine. So they took a much larger NIH experiment, and they had to only include people who had a very well-defined notion of where they're from geographically. So they removed all immigrants. In fact, they only kept the people in the data set whose 4 grandparents were all from villages within 50 kilometers of each other. Now, this is not Gaussian data. But what we can do is, I'm trying to make the point that these basic algorithmic problems like high dimensional mean and covariance estimation are very powerful from the sciences. They're not just problems that we want to study to prove theorems, but they're actually things which can change the way we do things in practice, which for me is what I call being prescriptive. It's about using mathematical tools to change what people use. And the question we can ask is now, could we have found these kinds of patterns in the presence of noise? So what happens when I take this high dimensional data set that's impossible to visualize in high dimensions and inject my own noise? Then I can do things like PCA still, and that is going to recover this horribly jumbled mess. I'm an American, so I'm not good at geography. Even I know this isn't a good map. But it's pretty intuitive that a small amount of noise would really mess up PCA because all of these outliers are correlated in some hidden direction. So they can very badly rotate the singular vectors until what you see is just noise and you don't find the scientific phenomenon that's buried in your data. You can take the same thing that you can take things that people have been using for decades that they thought was robust, but actually wasn't. Ransack, it doesn't work so well. You can do other things like there are these robust PCA methods based on semi-definite programs. They have a different sort of gotcha. They depend on the rank of the denoised matrix, which is oftentimes pretty large too. So it's a bit better, but it's still not good. And what we can do is let's pretend that our distribution was a high dimensional Gaussian. Let's robustly estimate its covariance in a way that's resilient to 10% corruptions, and then look at that estimated covariance sigma hat and take the top two singular vectors. And when we project the data on those two directions, we get almost the same map of Europe as if there was no noise. So just to put these two things up side by side, I apologize we lost Turkey, but Turkey was only 4 data points down here in the right left. So this, I think, is a very good proof of concept that these types of algorithms can really force us to rethink the way that we do things and give us new tools, which we're sorely in need of. So sort of looking forward, even just in this one direction of high dimensional robust estimation, I'd say that this is where these types of algorithms are going to make their money, right? Is an exploratory data analysis, because many high dimensional data sets, even though we don't have good models for them, they have 1D projections, random 1D projections that look pretty Gaussian. So being able to find the directions where the projection is non-Gaussian is very powerful. Even when you're not looking for corrupted data points, you're merely looking for other interesting phenomena in your data. And I would claim that, if we could compute the Tukey median and other things that were the promise of robust statistics, I think this is what they would have been doing all along, as they would have been applying it to exploratory data analysis, especially with the advent of modern machine learning. So let me briefly wrap up and tell you, this is one thread of my work, which I'm pretty excited about, high dimensional robust estimation. But more generally, I'm interested in theoretical foundations for machine learning. And that can mean a lot of different things, and it can connect with a lot of different areas in math. That's one of the things I'm usually excited about. So when it comes to asking some of the central questions in theoretical foundations of machine learning, one of the other themes in the types of things that I do is what's called beyond worst case analysis. You see, a long time ago, theoretical computer scientists asked machine learning researchers, what would you wish you could solve as an optimization problem? And then the communities went their separate ways, and we tried to solve the problems that they gave us. We couldn't, so we proved they were computationally hard. And then we went back to the ML people, and they're solving them anyways. So it turns out that, really, I think the way that algorithms can contribute to machine learning is by trying to hone in on what are the right models, because there's a negotiation between how exactly to set up the problem so that it's simultaneously expressive for the things you care about and rich enough, but also not so rich that it includes NP-hard problems as special cases. I've worked on things like non-negative matrix factorization and topic modeling that also turn out to be highly practical and with an emphasis on provable guarantees. I've also done a bit of work on designing new estimators. So these were some of the things that got mentioned in the beginning about mixtures of Gaussians. There's some interesting connections to analysis there, to the heat equation, to test functions and analytic number theory. And lately, I've been working a lot on non-convex optimization, so trying to understand what iterative algorithms, how they work when the geometric space is not simple, when it's non-convex, but maybe it has nice symmetries for things like matrix completion. I also think a little bit about computational versus statistical trade-offs. And I also think a lot about connections to statistical physics, because that's also a good way to make predictions about computational versus statistical trade-offs and study nice average case models. So I'll stop there, but let me summarize what I hope you got out of the talk, at least in the time where my daughter didn't interrupt me. So what I hope you got out of the talk was that I introduced robust statistics, how these problems are set up. And I talked about high dimensional robust statistics, and I gave you the first polynomial time algorithm for agnostically learning a high dimensional Gaussian. I gave you a general recipe for being provably robust, which uses restricted eigenvalue problems. And I'm going to close with the last question, which is practical robust statistics within reach? So thanks for your attention, and happy to answer any questions you might have.
All right. That's great. So are there any questions? Anybody would like to ask any questions about this talk or anything related?
I have a question. I wanted to ask just a little more about the algorithm that you described. Say, for example, with the identity covariance, where you're just computing the mean. After you do this first step and you throw out some of the data points, are the remaining data points going into the algorithm as if they were just data points from the beginning? Or do you remember and use like, oh, I threw out some things in that direction?
So that's a great question. So from a theoretical standpoint, I don't know how to analyze the algorithms any better to incorporate the old information about which directions I've explored. So we just throw them directly into the algorithm. That is what makes the analysis a bit nastier, is because then you have to worry about how those points are sort of affected by what happened in the first round. But one of the actual empirical mysteries is that it's really hard to cook up examples where the adversary adds a bunch of corruptions and they force you to explore a lot of different directions. So it's actually very hard to get the algorithm to have to do more than a constant number of phases, even though in principle, the analysis only says that you're making progress and you might need up to like D phases to really complete. I should mention that actually, so there are a few different algorithms for these kinds of things. Like the one that I described was, the one that's a bit more practical because you just have to compute top eigenvectors of various statistics. But some of the approaches that are closer to optimal for sample complexity, they're based on convex programming and semi-definite programs. So there what happens is a little bit different because you maintain weights along the points. So it's actually a sort of smoothly varying process where you're not actually hard throwing out points or keeping them in. So there you actually do use some of the dynamics about how you've updated the weights in the past to inform how you update them in the next phase.
Okay, that is helpful. I'm thinking about, since the adversary seems to be able to force you to sort of throw out data in some direction, that seems like you're losing information. I suppose because you know that the distribution is Gaussian, you're really relying on that. Like, for example, if the adversary, instead of adding false data, just could pick 10% of your data and delete it,
mm-hmm.
Would that be an easy problem to solve if you knew it came from a Gaussian?
Yeah, great question. So if the adversary could merely delete 10% of your data, that would actually get you epsilon times log 1 over epsilon close. Because see, what happens is the worst case, even if you think about it in 1D, the worst that the adversary could delete if they were only allowed an epsilon budget is they would chop off the tail. So what happens is that, within the proof of correctness for the algorithm, you have to show things like when you take samples from a nice distribution, every 1 minus epsilon subset of it would give you good empirical estimates. So if the adversary merely cut out some part of your data, that would actually be the easy case where you'd end up right up alongside these bounds. Now, it's true that even there, that's a great way to think about it, is you're losing information because you could in principle get epsilon close to the thing and not epsilon times log 1 over epsilon, and that root log comes from the tails. Well, that's where I'd sort of briefly mention that people proved computational versus statistical trade-offs. They showed that it's actually hard to get down to a constant times epsilon because you'd sort of have to really brittly fit the sort of Gaussian curve to your data to see that a tail had been lopped off.
Thank you.
Laura, you have a question? Please go ahead.
Yeah, I was curious about your synthetic experiments, or how you designed them or chose the corruption. I was imagining that for the different algorithms that you're comparing your algorithm to, that their worst case scenario would be very different, and so I was just curious how you structured the synthetic experiments and what you were really.
That's what I thought. I thought that would have to be the case too. So when I started off, the way that I was thinking about it was, all right, how should I mess up, off-the-shelf algorithms, which cannot find all of these corruptions? So my thinking was, let me add an epsilon fraction of samples from a distribution that doesn't have a second moment. So something like a Cauchy distribution, because then if you don't remove it, you can't even converge. Your empirical mean doesn't converge. So at first we tried doing that. That, did mess up things, but it turned out that doing something even sillier of just choosing a random direction with, no sense of what algorithm we're trying to break is trying to do, choosing a random direction and adding the corruptions right on the boundary of the sphere is enough, because then what happens is that most of the algorithms only see the data through random projections. And that part just completely vanishes because it collapses, it contracts by a root D factor. So what's kind of funny is that things like these ransack approaches, they work extremely well in low D because they're based on subsampling the data and then finding an estimate for the subsample and then doing that many times and seeing which of them are good estimates. But another way to think about it is that in high dimensions, you would need at least D samples from your distribution to have any sense of what's going on. And it would be incredibly rare to get a set of D samples that totally avoids the outliers. So those types of things are very easy to visualize in regression settings that, they would eventually find a good estimate. But all of that intuition is sort of misleading. And that's one of the funny things I find is that, robust statistics really had its heyday in the 60s. There were special years at Princeton, and Tukey got very excited about some computational problems there. But, after a while, people stopped working on it because they couldn't solve the algorithmic things. And to a certain extent, high dimensional machine learning has sort of gone on in spite of that without any confidence that what they're doing is correct. So one of the things I'm interested in, although the scientists really did not like this, was, I want to find some scientific applications. And at MIT, there's the Broad Institute nearby where they do, high dimensional genetics experiments and things like this. And they have these consortium data sets where they have labs around the country collect different pieces of the data. And the funny thing is there are a lot of empirical studies about how you create bias that way in the data collection process. Literally, if this grad student shakes the test tube twice and this postdoc shakes it 3 times, that's a big difference. But what consortium data sets do is they just lump all of the lab data together regardless of the lab's different procedures and try and do science on it anyways. So one of the things that I pitched to them was, well, let's take this high dimensional data set, look for the non-Gaussian projections, and see if I can reverse engineer which lab collected which piece of the data. And they did not like that because that meant that you have to be very careful what you're doing. So actually, I once had to give a talk at the JSON organization and someone made a wager with me that their methods worked because, you know, you would think if you're doing science and they weren't robust. And so I have a bottle of wine as a result. But I don't like wine.
Oh, no. Thank you.
Any other questions?
I have a question, just a little bit simpler. At the beginning, you talked about noise, but then you kind of shifted to adversaries. And the adversaries were allowed to add in 10% spurious data or something, whereas, you know, with ill intent, whereas noise we think of as being ethically unbiased, but present in all of the data at once. And I'm wondering if you could just talk a little bit about those two different models.
So that's a great question. So some of the ways that people formulate, I mean, you're asking the question, what is noise, which is an awesome question, right? Now, some of the ways that people model noise, especially in like, you know, more electrical engineering and information theory disciplines, is a lot of times they make another model about the noise. Now, this has its own limitations, and I can say something about that because I'll throw stones at some things I've worked on too. So back in the day, how Tukey formulated this when, you know, he had that special year with all the computational things, was he formulated noise as another Gaussian. So he revisited some of Pearson and Fisher's old debates about what are the most efficient estimators, and showed that when you add extra noise and it looks like a Gaussian, that other things like Edgeworth performs better. Now, the trouble with that is that that's what's called a parametric model, because there's still a small number of parameters that define it. So when you ask the question, what's the best you can do, you know, from a algorithmic or machine learning standpoint, you could always fit the model and the noise. And that's problematic because it leads to brittleness in a different way. It's just sort of pushing it in a different direction. And that is something that I think a lot about. Actually, I very quickly flashed, so of course no one saw it, but I think a lot about something called semi-random models, which are this cool way that you add noise on a distribution, but then you're allowed to undo the noise. And that can actually destroy a lot of algorithms that people use. Like people use things like matrix completion, where you partially observe a low rank matrix, and they assume that you observe uniformly random entries. Now, the funny thing is they do that out of mathematical convenience, but no one watches movies on Netflix by looking at a random movie. And when you then allow an adversary to show you more of the data, it's just showing you more of the thing you want to estimate, it destroys a lot of the algorithms that people use and have provable guarantees for. So that's partially why I formulated it this way, is that it was more in an agnostic sense, that I don't want to fall down the trap of modeling the noise. But the other, you know, good philosophical point is that outlier somehow has a negative connotation because it sounds bad, but outlier is oftentimes a very interesting part of your data. So that's why I think of it as something maybe for exploratory data analysis. So back in the day in robust statistics, they looked at outliers for measuring the speed of light, and you could always eyeball it and see which things were wrong. And they found that it was machine failures. But in high dimensions, we sort of don't really know what's going on. So corruptions are just a convenient catch-all that allows me to ask questions like, can I find them, so that I can see what I'm missing in my data.
Oh, really interesting. Thanks.
Yeah, I think, so since we already passed the time quite a bit, and so maybe let's end the discussion and question here. And if you have any question, you can contact Ankur, and he will be happy to talk to any of us. So thanks a lot. Thank you.
Especially once my kids are back in daycare.
Yes. Right. Bye, everybody.